Okay, so we are on to our next subject, which is AC motors. And just like DC motors, the idea of this electric motor is to take in electrical energy, in this case from an AC source, and turn it into mechanical energy, so mechanical motion, torque, on a rotor, which in our very simple AC motor here, the rotor is just a permanent magnet. All right. So as you can see here, we've got a couple of electromagnets on our stator. They're connected directly to an AC source. They're on the stator, so we can just wire them right up. There's no need for commutators or anything else that can make this some sort of sliding connection to the rotor. And as it says here, so as the current oscillates back and forth, the electromagnet polarity shifts as well. And you understand that, right? If we change the direction of current through an electromagnet, then we would flip a north pole for a south pole, right? We'd flip the poles back and forth and back and forth. And the idea with an AC motor, at least this very simple type, is that oscillation in the magnetic field is going to alternately push and pull the north and south poles on the permanent magnet rotor, and it's going to cause rotation. So just so we have all of our bits and pieces labeled here, so we got a permanent magnet on the rotor, got our AC source, usually an AC generator at its source, but this could be, plugging it into the wall of our home or apartment. And on the stator, we've got our electromagnets, just two of them in this simple AC motor. Okay, so let's get an idea of how that alternating current causes an alternating magnetic field on the stator, which then causes the rotor magnet to follow that oscillating magnetic field. In fact, what we usually talk about with AC motors is the idea that the direction of the field rotates, so goes around and around in a circle around the stator. Now here it's going to be a little more difficult to see because we only have two electromagnets, but when we get to the example that we'll have at the end of this video where we have four electromagnets, the idea of rotation, quote unquote, of the magnetic field created by those electromagnets should be a little clearer. Okay? So, just to orient you here, let me switch my pointer to something that I can draw in. Let's go with green. All right, so what we've got here is a bunch of little snapshots at various points during one rotation of the rotor. And we're going to make our first snapshot of a point where you've got the AC source. Okay. At this instant in time, it is, you see a little red dot here, just creating 0 volts of difference across the circuit. That, of course, means that 0 current flows in that circuit, and so we wouldn't expect any magnetic field at all, and the rotor would feel no force. Right? However, if we play the tape forward a little bit, if we fast forward a little bit so that we are farther up the input voltage, so we've got voltage versus time here of the AC source. And if we play that forward just a little bit, so we're coming up the side of the curve, say we've gone through about 45 degrees of the whole sinusoidal oscillation, okay, so about 45 degrees of that, maybe a little more. And that corresponds, as it turns out, with this so-called synchronous AC motor to about 45 degrees of mechanical rotation of the rotor. And as for why it's going to rotate in that direction, well, notice that here the position of the rotor is this. And so as the voltage applied to the circuit rises, that means the current, so this is indicating I, the current rises. And so this current is going to create, if you check the right-hand rule, a north pole on this electromagnet closest to the rotor. Of course, would be a south pole over here. And on this one, if you check your right-hand rule, you get a south pole on the end closest to the rotor, and that would correspond, of course, to a north pole on the end that is far away, and we don't really care about that much. Okay, So this means that the direction of the magnetic field here is from north to south, in terms of the field created by the electromagnets. But I think mostly we just want to think about the very simple rule that we learned about magnets and how poles interact right at the beginning of our discussion of magnetic field, which is that like poles repel, so this north and this north are repelling each other, which is going to cause rotation of the rotor this way. And this south and this south are repelling one another. So that's going to cause rotation of the rotor in that same clockwise direction. Okay. Now, if we go a little bit farther, so we've gone through about 90 degrees of our sine wave, so we're right up at the peak of our input voltage, and that corresponds to about 90 degrees of rotation in this simple motor. And that means that the current's still going in the same direction. If you go back here and you come forward, you see the current is still going this direction through the circuit. And so, label the current again. That means that this north on the left is attracting this south pole, and it's still repelling this north pole. And this south over here on the right is attracting that north pole, and it's repelling that south pole. Okay, so we're still getting clockwise rotation for our rotor. Okay, going a little bit more quickly now. If we go another 45 degrees, we've gone through another 45 degrees of the sine wave. The current is still going the same direction, though I guess would be a little bit less since we have less voltage at this point. We have less current, but that maintains the direction of the magnetic field, maintains this pole and this pole, and so they still attract here, attract there, repel here, and repel here, although I guess those souths are pretty far away. Okay, we still get that clockwise torque. And so when we come to the point where the voltage has gone away for an instant, right, we're right here on the axis, so voltage is 0, so current is 0, so there are no poles on the electromagnets. And at this point, I guess the rotor would just sort of be coasting, but it has this clockwise rotation. It will have felt forces to cause it to have a rotational velocity in this direction. All right. So we can play a couple more frames. So if we go a little bit farther along, so here we've gone through about 180 degrees. Here we've gone through a little bit more than that, almost 270, a little bit less. But you'll note that north, remember, it was on the left, and south was on the right when we had positive voltages on our axis. So when we come down here and we have negative voltages, that just means that the current has changed direction. So now the current is going this direction through the circuit. That creates a north pole on this electromagnet where it used to be a south, and a south pole on this electromagnet where it used to be a north. And that, as you'll notice, now that the rotor has come around, is still causing, right, north to repel north, south to repel south. South is being attracted by the north on the right, the north is being attracted by the south on the left, and you still get this nice clockwise rotation. So remember that we had to have a commutator with a DC motor to get that kind of switch. Well, here with our permanent magnet on the rotor, we switch our poles for free, quote unquote, because of the oscillating current given to us by the oscillating voltage of the AC source up here. Okay. So, and then of course, if you want to complete the whole cycle, you've gone through one complete cycle of the sine wave, and you've gone through one complete rotation of the rotor. And in this kind of motor with two electromagnets and a permanent magnet on the two electromagnets on the stator, permanent magnet on the rotor, you get one oscillation of voltage equaling one rotation of the rotor. Now, these certainly get more complicated. I've borrowed a diagram here to show a dual phase motor. And if you're in my lab class, we'll talk a little bit about phases in the last lab activity. The basic idea is shown here in this graph on the right. And you can see that, say, phase 1, the vertical pole, so the thing that's red, here, I can fill that in for you. Red. So this voltage would be what's going to the vertical pair of electromagnets. So here and here. And the, hold on a moment, get my other ink color, get some blue. So for the source 2, so phase 2, it's the same sine wave, it's just offset in time. So where the red is at a peak, right here, then this one is at 0, and when this one is at a peak, the red one is at a 0, and so on and so forth. So they're just kind of shifted in time relative to one another. The thing that this buys us in an AC motor is that you'll remember way back at the beginning of this thing, I gave this rotor like just a little bit of tilt. It's not straight across, it's just tilted just a little bit, and that's so that when the voltage starts to rise and the current starts to rise, then you get this clockwise rotation. Right? If I had started this the other way, like if I had tilted it so that it was like that, for instance, well, then you would get rotation in the opposite direction, and there's really no way to control that in this kind of motor except by where you start the rotor position. In this kind of motor, where you have a dual phase, there are more advantages to this, but here you actually get a predictable direction for the rotation. And you can see that sort of in these cartoon pictures up here at the top, where they're showing you what the magnetic field looks like and what the rotor position looks like at each moment in time. And you can see also here the so-called rotation of the direction of the magnetic field created by the electromagnets on the stator in this more complicated AC motor. Right now, there's no current being applied to the horizontal set of electromagnets, so there's no poles there. And for the other one, right, the vertical one, the red trace here that I've colored in, phase 1, vertical poles, well, they're at their maximum. So they're creating a really strong magnetic field, goes from north to south, and so the gray arrow here shows you the direction of the magnetic field created by all of the electromagnets on the stator. Now, when you come over here to the second one, you can see that at this point, both of them have current running through them, right? Both above the axis by some amount. And so they both have north and south poles on the horizontal pair and the vertical pair of electromagnets. That means that the net magnetic field is sort of off in this direction. And as you come over here to the third, number 3 here, well, then, okay, well, then the vertical pair is off because you have 0 voltage. And these are at their maximum. So we have magnetic field in this direction, and then magnetic field in this direction, and then magnetic field in this direction. You can follow the whole thing around if you went through a whole cycle of the voltage. But you can see that the direction of the magnetic field created by the stator is rotating. And in this type of motor, which is called a synchronous AC motor, the rotor, whether it's a permanent magnet or whether we're somehow routing power to it and it's an electromagnet, is going to follow the direction of the magnetic field. It's in sync with the rotation of the magnetic field created by the stator. Okay, so we'll talk a little bit more about the advantages of these dual phase and actually 3-phase motors as well next time, as well as looking at the most ubiquitous form of AC motor, which is called the induction motor. We'll learn a few of the basics about that. Thanks for listening.